So before we do more example problems of reactions and predicting products, I at least want to kind of expand our world of reactions first, just so I can tackle a couple of different concepts at one time. So the next reaction that we want to focus on is one that involves ozone. Yes, people, we use ozone in a laboratory. We can easily do it. This ozone can be used for a particular type of purpose in the alkene world, and we're not destroying the ozone layer when we do this, but we are using ozone in order to make this process happen. All right, so what goes on in an ozone reaction? Okay, so we know that we're going to have a double bond. So here's two carbons. They're involved in a double bond. I'm just going to write the little prong feet on each one of those, and we're going to draw ozone, which hopefully you understand is O3. So sometimes they'll do O3, and sometimes they will write down this fancy word that's called ozonolysis. Okay, so ozono represents ozone. So we are using ozone to lysis something. Well, lysis means to cut. That is what that word always represents, it seems like, in a science course. Okay, so what are we cutting with ozone? Because that's what that translates to. What we're cutting with ozone is a whoop, there you go. Notice how I made the cut. It splits those carbons down the middle that is involved in the double bond, and it separates them out. So what we end up doing with ozone lysis, or with the incorporation of ozone to a double bond, is that we have this carbon that was involved in a double bond, but now it's not really attached to anything. Okay, and then over on the right hand side we have that carbon with the feet, and that also was involved in the double bond, and that really isn't attached to anything right now. So we split those two pieces in half, part 1 and part 2. They're not sequels. Part 1's always better. So we need something that will go in and take the place of that double bond that carbon shared with the other carbon. And ozone does a great job for us. What happens is that ozone is a 3 oxygen containing ring, almost. Kind of a ring, not quite, but it could make one in the mechanism, and that's what you'll see. But in the end, what I want to show you without mechanisms, in the end, what happens is that one of the oxygens will go here from the ozone, and another oxygen can go there. Folks, that's it. There we go. That's all we need to talk about. Ozone lysis uses ozone, which is O3. It shaves the double bond down the middle. It breaks them up into 2 pieces, and oxygen gets sandwiched onto those areas where that double bond was at one point in time. Now, in doing this, we are going to be introducing 2, maybe 3 new functional groups that we need to talk about. So, functional group number 1, what is there? Well, something that we've seen before. This, think about C double bond OOH, right? We had that C double bond O there, but we called this a carboxylic acid. All right, well, we don't have the OH here this time. We just have the C double bond O in each one of these cases. Well, we have a term that we use to describe this relationship, and we call this a carbonyl. Carbonyl. That is a carbonyl functional group. Carbonyl groups are probably one of the largest family of functional groups that are out there. They contribute to so many different functional groups at so many different points in time that carbonyls are very, very common. And we already have talked about a type of carbonyl, and that was a carbonyl with an OH group. And this was called a carboxylic acid. Okay, this is something that we've already seen, we've already discussed. Well, we have 2 other possibilities as of right now that we can talk about carbonyls. There's many more than this. But sometimes when the carbonyl forms, we could have a R group to the left and an R group to the right. Okay, so that means that this group would have carbons flanking both sides. In other words, this would be almost like CH3 here and maybe a CH2 and a CH3 here. Therefore, when this carbon double bond splits, it's still a CH3 there. It's still a CH2, CH3 here. That does not get touched. The only thing we do is add an oxygen onto this side. Well, that carbon has a carbon to the left and a carbon to the right. Okay, so whenever that happens, we have a special term that we use for that particular type of carbonyl, and we call this a ketone. Okay. Next, we have another carbonyl that could form. This is slightly different. We could have maybe a carbon over on the left-hand side, but on one side of the house, it's just a simple O hydrogen. That's all there is. All right, so in other words, that would be like saying here's CH3 and here's hydrogen. I mean, we've seen those types of groups on carbon double bonds before. We know how to name them. We know cis and trans and E and Z. That's nothing new. And then over here when this forms, those do not get touched. They're still there. The only thing that we've done is slapped an oxygen onto here. If we do that, this carbon is not flanked by two others. This carbon is attached to one carbon on one side, but on the other side there's a hydrogen that's there. So whenever we get a functional group that looks like this, where it's a carbonyl with a hydrogen on it, we call this an aldehyde. That is the functional group or term that we use for that functional group. So folks, we're going to add these to our functional group vocabulary. Alcohols, ethers, halogens, carboxylic acids, amines, carbonyl, ketones, aldehydes. The list is just getting bigger and bigger, and that's the way organic is. But you're going to do it. I've got faith in you. You can keep these things straight. You're going to learn them. I know you will. You're good like that. So ozone splits the double bond, breaks it off into two pieces. Oxygen goes on each one. And then we have a chance to form maybe a ketone type of molecule or an aldehyde type of molecule. Also, I want you to keep in mind that if this was just another hydrogen, that is still going to be classified as an aldehyde. Okay, so if it has a hydrogen, whether it's one or two, we still call it an aldehyde group. Now let's take a look at the mechanism here. This is at the very bottom. I don't really want you to pay too much attention to this. It gets very complicated if you're not careful. Here we see our double bond in the very first step, and the O3 molecule comes into play. Notice that the O3 molecule is a nucleophile and an electrophile both. It carries a negative and positive charge. So just like with some of the other later mechanisms, this whole thing just happens at one time. The double bond breaks and it forms a single, and that bond will open up to that oxygen and carbon, and they will attach. And then over here, that double bond, because that oxygen's taken on an extra, gets shoved to that oxygen because it's slightly positive. And then this carbon and oxygen share a bond as well. And we form this cyclic kind of intermediate that happens here. So that is not going to stay around very long. It's going to rearrange on itself again. And that's what you're seeing in this step. And then finally here. Well, when this begins to form, we call this an ozonide. When that begins to form, we need to break that down and release the oxygens that is present. You can almost see the formation of a carbon double bond, and a carbon double bond may be there, right? So we need something to cleave all of those bonds and make this process happen a little bit better. And there's a couple of ways that we can do it. We can use zinc, or we can use this sulfide-based compound, and either one of those will work. So if you see this in the ozone lysis, that's really all that they're doing. It's just the second set of reagents that we can throw into the flask in order to confirm, yes, we want the formation of the ketones and or aldehydes to show up. We want to complete the ozone lysis at this point. So it does need a little bit of extra help. It's not just ozone and that's it. We do need a little bit of extra help for this process to go on. Okay, here's a couple of examples with the ozone lysis. Also, I want you to notice the temperature that has to take place here. The temperature that has to take place is negative 78. What? Negative 78? That's like wintertime in Wyoming. Okay, well, negative 78 is a very deep freeze. You know, I say that kind of lightheartedly, but we do need super, super cold temperatures in order for this to work and go forward. So is it practical? The answer is no, not for most labs. For most labs, this is not a practical mechanism that we can do. It's not a practical reaction that we can do. Under certain labs, though, that have the necessary equipment to get down to negative 78 and to allow this reaction to happen, then they can do this quite easily. Of course, it's got to be done because otherwise we wouldn't know the mechanisms of them. So this is how you're going to see the ozone lysis represented in the world of alkene chemistry. So you're going to see the alkene, which has the double bond, and that double bond is going to be broken, but this time it's going to be chopped in half, and you get two pieces here. This carbon to the left has a methyl and a hydrogen, and look, it still has a methyl and a hydrogen that's there. The carbon to the right, it just so happens to have two ethyl groups. That's perfectly fine. So on this side, there's still two ethyl groups that we draw. The difference is that we draw an oxygen there and an oxygen there. In order for that to happen, we have to have ozone. That's negative 78. And in round 2, we throw in a sulfide group, dimethyl sulfide. Why do you think I called it that? 2 for di, CH3 for methyl, S for sulfide. Dimethyl sulfide. So if I look at this arrangement, this is a carbon with an R and an H. That's the aldehyde. It just so happened to have an aldehyde. Maybe it doesn't, maybe it does, but this one it did. And then on this side, we had a carbon that was flanked by two carbons, one on each side. And that's what we call the ketone. Down here, same kind of process happens. We take the double bond, we shave it in half. There we go, it's ozone lysis. We get this cyclopentyl ring, and we see the cyclopentyl ring still there, except the double bond that was to a carbon is now to an O. On this side is an isopropyl group, 1, 2, 3. So I still see the isopropyl group that's drawn. And instead of a double bond to that ring, it's now a double bond to that O. Again, ozone's required, negative 78 required, but this time they chose zinc instead. No rhyme or reason. It basically gives you the same type of products no matter what you do. Types of compounds that form here just so happens to be both ketones. This C double bond O, that carbon has a carbon to the left and a carbon to the right, so therefore this is a ketone. This one, this carbon involved in the carbonyl, has a carbon to the left and a carbon to the right, so therefore that's also a ketone. Down below, we see another alkene. That alkene bond's going to break. There we go. Ozone, negative 78, sulfide group. Not a big deal. We know ozone lysis is going to form. Two pieces happen. What are those pieces? They try to trick you here. Keep in mind this carbon has this propyl group as well as a hydrogen on it. So here is the propyl group and the hydrogen. They've just drawn it a little different that way. Making sure you're paying attention. That's what they're doing. And then over on the right-hand side, this carbon is attached to two hydrogens. So they draw a hydrogen up and a hydrogen down. What types of compounds are formed here? Well, this carbon has an R group on one side and an H on the other. Because it has that H there, this is an aldehyde. And then this carbon, it has a H directly attached to it. I can stop there. This is also going to be an aldehyde. We're not going to really learn how to name ketones and aldehydes right now. That's really part of a second organic chemistry class. And this is just where we're going to stop with as far as labeling them. We can at least classify them. We can call it a ketone. We can call it an aldehyde. But that's about as far as we're going to go with it. We're not going to name these products like we've done before in the past. But folks, this is the example of ozone lysis. At face value, it's a pretty simple reaction. Okay, look at the double bond, cleave it in half into two pieces, and slap your oxygens on there. That's all that we have to do. But as far as mechanism goes, the mechanism is quite disturbing, and it's something that we don't really like to see and don't really like to talk about, and you'll probably will never see it again anyway. All right, so that's where this video is going to stop. In the next one, we are going to do some examples. We're going to lead up to this point, kind of figure out what they want us to do, look at some more reactions, forming products, maybe naming those products, and that way you can become more and more comfortable with this material. So that's where I'm going to stop this. I'll see you next.